Good morning, everybody. My name is Alex Bassini. I'm the Business Development Manager here at AWC Solutions. Welcome to now episode number 25 of this webinar series. Today we are joined by Dr. Ruth Roxburgh. She is joining us here from AWC as well. She has a PhD in water and wastewater treatment, and she used to work with CHM2 Hill. I can always chop that up. We have covered wastewater before. This time around, we're going to be focusing on the membrane bioreactor. So it's a very specific component of how we do this. If this is your first time, welcome. Like I mentioned, a shout outs to, we have a new group from Mexico that's tuning in. So buenos días a todos. This is some of the webinar series that we've been doing in the past. If we've missed any of them, they're all available on the YouTube channel. You can go over them. So just a quick little background on AWC. We have been around now for 40 years. We have close to 600 plants worldwide now, expanding into Latin America and doing, of course, more work outside of North America. We do split everything up into multiple categories. That includes potable, wastewater, and skid-mounted systems. Today, of course, we're going to be focusing on the wastewater side of things with the membrane bioreactors. And with this, I'm gonna shut up and I'm gonna leave this over to Ruth. So go ahead, take it away.
Good morning, everybody. So I've got quite a lot to cover, and trying to make sure that I can address a range of backgrounds. So hopefully, is my screen showing now, Alex?
It is.
Yes, we can see it.
Okay, awesome. So just a very short time to cover a lot of information on MBRs. We'll talk about how they work. Submerged versus external, what are the advantages? And I also touch on some disadvantages, to be fair. And some key aspects of sizing an MBR plant. So just to just to go over the traditional way that biological treatment systems work. We have a biomass, and that is separated from the liquid and the solid stage after the treatment process, traditionally using just density difference between settling and the density between settling or flotation of the particles.
All right, let's give it a couple minutes. We're having a little animal interruption. This happens when we're going live. All right, here we go.
And so typically the particle size removal will be down to about 50 micron. Typical effluent TSS will be around the 10 to 20 milligrams per liter, as long as everything's running well. Getting a bit of feedback, Alex.
Yeah, we're fixing it on our end here. Go ahead. See if that's better.
Okay. I seem to be having some technical difficulties with my laptop here, sorry. Do you want to switch to the next slide, Alex?
Sure, I'll take it over here.
Yeah, my computer's getting stuck, sorry.
No worries. All right. There we are.
Okay, thanks. Okay, next one. So in contrast, the difference with a membrane bioreactor is that it takes away the gravity or density separation aspect of the solids and the liquids. And the membranes actually act as an absolute barrier for solids removal. So this little diagram just shows how the solids stick on the outside and the clean water goes in through the inside of the membrane. And so that's how the membranes are different. They are an actual filter, so they have different pore sizes. So in contrast to gravity separation, the pore sizes range from 0.1, which is generally we call microfiltration, down to the 0.04 micron, which is generally the range that we are operating at in ultrafiltration MBR systems. Because most protozoa and bacteria are in the range of about 0.2 to 10 microns, the membranes therefore do actually give you pathogen removal, which you really don't get with gravity separation. And typically effluent TSS will be less than 3. Usually that's the detection limit of your lab samples. In the MBR, the solids stay on the outside and the water flows in through the membrane. That's a very typical way they run. Because the solids are being trapped on an actual surface, the membrane surface does require cleaning. So this is different to gravity separation, where there's really no cleaning. It's just using gravity and density separation. And because you are actually have a filter, the water has to be pumped through the filter, whereas gravity separation, it just overflows the tanks. And so usually the water is pumped or pulled through the membrane depending on the configuration. Now the one key difference in design is that in this state, the excess flow has to be diverted. So because you're pumping, you can only pump at a certain rate through the membranes. If you have a high peaking flow, a big storm event, or even just very high diurnal peaks that come in, and your membrane flux and your membrane pump is not sized to handle it, then you do need to have some equalization, or your membrane tanks will overflow. So this is another key difference between gravity separation. So just going over some of the configurations, there's generally 2 configurations. One is submerged membranes. This is sort of the most well-known application of membranes. We've got a little picture on the side here that shows a membrane module. They're usually in some sort of frame, and these frames are dropped into the tanks that you can see on the bottom half of this picture. And these membranes will sit in the mixed liquor in the tanks. Generally, they're hollow fiber or flat sheet, sort of 2 configurations of how the membranes themselves are made. And generally, they are air scoured to try and keep the solids from sticking to the membrane sheets. And these type of membranes run on vacuum, and they are very sensitive to the transmembrane pressure. So if you pull too hard through the membranes, they will or can delaminate or collapse. So it is a very key design parameter. Normally they will backwash or do a rest every 1 minute in a 10-minute cycle, so that they clean themselves as they're running. And generally you will need to CIP them depending on your water quality every 3 to 6 months. Some manufacturers require a chemical soak in the tank, so you drain down the tank, fill it with clean water and chemicals. Some manufacturers don't do that and will just backwash the membranes and soak them with chemicals inside the sheets themselves. One of the key differences between that and the external membranes is that the submerged membranes will run at a lower flux just because of their lower pressure. So they will usually run around 15 liters per meter square per hour, or 9 GFD is typical for a sort of average flow design. External membranes are not in a tank. That's the key difference. They're usually in some sort of housing, like this one here shows you in a tube. And they come in, again, flat sheet or tubular. The picture here is what we call tubular membranes. They're sort of like very big straws, and the wastewater will be generally on the outside and clean water sucked into the inside. These are different because they don't need a tank, so you don't have the cost of building tankage for them. They use cross-flow velocity to keep them clean, so usually they don't have an air scour requirement. There is one manufacturer that does use air scour. So because you're pumping through them, the pressures are usually higher, and they're designed to run at high transmembrane pressures, typically 20 to 60 psi. And again, most of them will have an intermittent backwash. Usually the cycle is longer. It's usually 1 minute every 20 to 30 minutes, so less frequency of backwashing. And you can run at a higher pressure through them. Well, you do run at a higher pressure through them. So the CIP here is different, and it is generally a much smaller volume, because instead of filling an entire tank, you just fill in these pipes or vessels. Because they do run at a high pressure, they do have a much higher flux, and this is one of the key differences. So they will run at 75 to 90 liters per meter square per hour, or 45 to 55 GFD is typical for most MBR applications, so that you can actually get more flow through a much smaller membrane surface area. However, historically, they have had a higher energy demand because there is a higher pressure drop to get that high flux. You're pushing the water through the membrane at a much higher flow rate requirement. So that is one of the key reasons why they have not become as popular as the submerged membranes. However, we did want to bring to your attention membrane that we have been using here. It's been developed in Canada by some of the original membrane experts from Xenon. And this is a flat sheet membrane, which is different to the traditional external membranes. They've taken a flat sheet but put it in a pipe. And because of their configuration, they run at a much lower cross-flow velocity than the traditional tubular membranes. So they run about 1 meter per second versus 4.5 meter per second. And their typical TMP is 10. We allow designs up to 15 for sort of a safety factor. So this, as you can see, much lower cross-flow, much lower TMP than other external membranes with the tubular setup. And they've also used a double backbone polymer PVDF and polycarbonate membrane layer, which extends the strength and the life of the membranes. And one of the really interesting things, they have actually used these membranes in thickening applications on digesters, and TSS up to 15% through the membranes. And these differences have provided them the energy consumption very similar to submerged membranes. We recently did a project where we were going to use submerged membranes. We've switched them to these external membranes due to some specific site constraints, and the energy consumption is actually lower than what we had originally planned for with these submerged membranes. They do have a very high packing density, and that is a big advantage. So in the specific project, we were able to reduce our footprint. So I think there should be a picture on this one, Alex, if you wanted to scroll till we get the picture up. Yeah, so this is the installation that we have just got up and running. As you can see, these external membranes, because they're not in a tank, they're very easy for the operator to access. He can just walk by, check them, see the pressures. If he needs to change one out in the future, it's very easy to change out. In this situation, the operators were very excited that they had submerged membranes on an older plant, and they were very excited to get these new membranes that now they can get to very easily, check very easily, They don't need cranes to remove them. And this is a very compact design. So in terms of footprint, total footprint with the pumps, with the CIP, and with the membranes, these were about half the footprint that we had originally planned for with the submerged membranes. And just one other thing on the external membranes, they are for cold climates very operator friendly because everything's in a building. You're not worried about the temperature impacts of tanks outside and cold wastewater. And that was one of the problems that the operators at that site had been having. So the advantages of MBR compared to clarification. Once you have freedom from gravity separation, it really changes the game for activated sludge design. We can run at much higher biomass. Typically in a traditional system, you'd have 3,000 milligrams per liter of biomass. Here you can run at 10,000. So that gives you a much smaller footprint because you have a concentrated biomass. It can handle flow and load variations better. One of the key problems we find with gravity separation is that it is very sensitive to pH. We get things called ashing on the clarifier, where your pH varies through seasons and ammonia loads and alkalinity. And on membranes, it doesn't matter at all. So your effluent quality is very stable. And I have a picture of membrane effluent here in this picture, and it's in a bottle, and really you would not know the difference whether this was drinking water or wastewater. You wouldn't want to drink it still, but it really is very, very clear. It's very good quality water. And because your water quality is that much better, you do also get much better disinfection. You'll get less phosphorus in your effluent from just lack of TSS. And if you are looking at reuse, then definitely membrane is the way to go. And another advantage is that you do get thicker sludge going to your dewatering or digestion just because your biomass is running at a higher concentration, so you'll have a lower wasting volume, and when you do waste, it is thicker to start with. But to be fair, there are disadvantages. There's no sort of silver bullet, I guess, in wastewater treatment. So you do have to equalize your peak flows, as we talked about. It is an absolute filter, and anything that can't be handled by the membranes and the pumps has to be diverted. It does require very fine screening. And generally, we now recommend 1 millimeter screens. And a rotating fine screen, what we have found is that static screens, the hairs and fine things do just float on right through and can still cause problems. This picture is a picture of foaming. And foaming will and can occur on any wastewater plant, not just MBRs. MBRs do have a tendency to have more issues with foaming, partly because you have a higher concentration of biomass, and also because usually your food to mass ratios are lower just because of that high concentration. Aeration is quite vigorous in your membrane tanks. And one of the key things that sort of gets overlooked in MBR design is surface wasting. So your filamentous bacteria, bulking sludge, tends to be at the surface. Most people in MBRs will waste from the bottom of the MBR tank or from the recycle line and forget about surface wasting. So there's no way for these filamentous bacteria to actually leave your tanks. So surface wasting is a very important consideration for membrane design. One of the other disadvantages you can run into if you're looking at nutrient removal, where you need anoxic tanks and recycle streams, is the DO in your membrane tanks is usually very high. It can be like 6 milligrams per liter. So you do need to extend your anoxic tanks or allow for de-aeration so you don't impact your nutrient removal. Generally, it does have higher operating costs. You do need to clean the membranes. there is extra power for aeration or the cross flow, and you do need to consider membrane replacement. Generally, we would budget for around every 8 years. There are installations which do run at 10 to 12 years. Just really depends on how well you take care of them and the quality of your wastewater. So just a few pointers on sizing MBRs. Some of these we've talked about already, but we do need to consider equalization, especially if you have high diurnal peaks, which often on smaller towns or small developments, you will find very high diurnal peaks. And you also need to make sure that your peak day and peak week flows match your membrane peak flux rate so that you don't get premature fouling just by trying to push more water through than the membranes really should be treating. Your inlet screen, you really need to size for peak flow capacity. This is just a picture of inadequate screening, what it does to your membranes. So you really want to make sure you don't have overflows bypassing your screens. Your pore size, we recommend, should be about less than half the spacing between the membrane sheets or tubes. And generally, we now recommend 1 millimeter spacing. Aeration is a very critical factor for biological treatment. One of the aspects that has to be considered for aeration systems with MBRs, because your biomass is so much thicker, your oxygen transfer efficiency is lower. So usually your alpha factor, which is your clean water to actual oxygen transfer efficiency ratio, we use about 0.45. So that's quite a lot lower. Normally in conventional activated sludge, you would be at about 0.8 to 0.9 on the alpha factor. And the other thing that needs to be taken into consideration is your maximum oxygen uptake rate. When membranes first came out and everyone was pushing the concentration limits in the tanks and saying, oh, my membrane can handle, 15,000 milligrams per liter of biomass or 20,000 milligrams per liter. And everyone thought that meant your tanks could just keep getting smaller and smaller. But empirical testing has shown that there's a maximum uptake rate. So you can get to a point where you have too many bugs in a given volume and they cannot consume the oxygen fast enough just because there's not enough oxygen for all these bugs in there. So when we look at sizing the retention time, you have to take into consideration that there's a limit to how much available oxygen is in any given volume of your tank. So we express this in grams of oxygen per meter cube per hour. And that's a key factor. So you get to the point where really you'll find that aeration systems can't handle much more than 10 to 12,000 milligrams per liter of biomass reliably. And then when you get into membrane design, they all have very specific flux parameters, pressures, ways of backwashing. Those all have to be very specific to the membrane you're looking at. You do need to look at the cleaning, the backwash, and the CIP. And like we mentioned before, the wasting, and especially on the piping and mechanical systems, because it is especially submerged membranes are aerated, you do need air handling pumps. You need to deal with potential for air locking in your piping. So these are all critical factors that have to be designed in so that your system works reliably.
Excellent. Right on time. We're right at 24 minutes.
No, sorry, that was a lot to try and cover in a little time.
Yes, it is. So we're going to open it up for some questions. There's a little echo there. So if anybody wants to put something in the chat box, or if you want to put it in the chat box, or you can turn on your mic and your camera, feel free to jump out right in. I do have a couple questions, so I'm going to start on my end. So the first one I have is, you had mentioned there was foaming. So with the foaming, how would that change between a submerged membrane and an external membrane? Would you still see the same amount of foaming on either one? Oh, sorry, you're on mute, Ruth.
Okay, don't know how I got on mute there. Yeah, with submerged membranes, there is much more vigorous aeration in the membrane tank than there is in the aeration tank. So we have found that the foaming tends to be worse with submerged membranes, largely because of that. In external membranes, the membranes are not aerated, they're in a pipe, so you don't have that same issue. However, any MBR, you do have to do surface wasting, and if you don't, you will over time get a buildup of the filamentous and bulking bacteria, and you will still get problems in your aeration tank if you don't account for that.
Now I'm the one on mute. Okay, I have a question here in the chat. It says, as shown in the submerged configuration, how does the external setup handle the severe fouling issues?
How does the external membrane handle severe fouling issues?
Yes.
Yeah, the submerged membrane, it's the same really for any membrane. You really have to have good screening up front. One of the differences, any membrane that's potted or sort of comes together at the top, like the picture I had, will get more fouling just because the air is moving up, and the potting and the way everything's sort of closed at the top just traps the solids. So flat sheet membranes in general don't trap solids because they are open at the top. So you will get things that can get stuck or just, very sticky biomass that sticks to them. But it will have less issues with fouling. And the same with submerged membranes. You're flowing at a very high cross flow velocity. There's much less chance of things getting stuck in there. And anything that's a flat sheet is generally handles fouling better than a tubular type membrane.
Of course. Okay, thank you, Ruth. Well, we don't have any more questions coming in. And if we do, if anybody wants to stick around, we'll open it up.
I think there was a couple more questions, but I don't know if you want to.
You're right. There's another one there. Okay, go for it. So Andrew asks, submerged flat plate, one of the claims for BOD removal is that biofilm on the membrane. How much of this is a factor for the submerged flat sheet versus the external membrane?
Well, really, that I found that any membrane will get you very good BOD removal. The soluble BOD is usually gone within a matter of probably a half an hour or less. So most of the BOD that comes through is actually more related to sort of colloidal or solid BOD, which takes longer to break down. So that's where any membrane will perform much better in BOD removal than an activated sludge with clarifiers. So for example, I've started up membrane plants and activated sludge plants, and an activated sludge plant with a clarifier, we have sometimes been 30 days or more before we've got to our permitted levels of BOD, sort of usually 25 BOD. And I've started membrane plants, and we've been in compliance, less than 10 BOD, like the same within 24 hours. So it does give you a huge advantage for very fast turnaround on BOD removal for any membrane.
So we do have a couple more questions coming in, but we are hitting our time limit, and I promised everybody 20 minutes, and we're going a little over. So if you want to stick around, we can go back and forth a little bit more with Ruth. Ruth, thanks again for coming on. We are now changing this over to the 2-week format. So in 2 weeks, we're going to have a company coming out to us from out of Portland, Oregon. We're going to be touching PRV, which is pressure recovery valves. It's a little different than, we're looking at real treatment. We're doing more of energy recovery. Before we sign off, I do want to remind everybody that March 22nd is World Water Day. We're not here to recognize the importance of water once a year, one day a year. We're here to do it every day. However, I do want to leave it off with 4 questions that I think we should be asking ourselves every day. They're pretty basic. It's, what does water mean to you? This is kind of the theme for this year. Why is water important to you? I think that's a big one. Of course, what do we use the water the most for? You've got, whether it's commercial or industrial or municipal, there's always going to be the largest amount of water we use. And of course, how does water affect our food? Food sources is one of the big ones there. So I want to thank everybody again for tuning in. You will receive a link to the recorded video if you want to follow up. If you have any more questions, you have our emails, both Ruth and I's. So please make sure to keep in touch. For anybody that wants to stick around, you're welcome to, and we can do a couple more questions. So with that, thanks again, and see you next week.